Welcome everyone to this second day of our first Corrosion and Materials Degradation web conference. We will start today's program with session 4, entitled Composite and Bonded Structures. And this session will be chaired by Professor Luigi Calabrese, who is a professor at the Department of Engineering of the University of Messina in Messina, Italy. His research focuses on functional materials and advanced composite materials, coatings, materials corrosion and durability. So Professor Calabrese, the session is yours.
Okay, thank you, Anna. Thank you to everyone. The session of today is characterized by 5 talks, and the first talk is mine. The first talk have as topic bearing performance of a pin and hybrid composite edged in a salt fog environment. Now, concerning the idea of this activity is to study the bearing behavior of hybrid, in particular in this presentation of glass flux epoxy laminate edged at different edging time in a salt fog environment in order to assess the mechanical performance and the failure mechanisms of the pinned joints and how these parameters are influenced by the joint geometry. This activity is finalized with an experimental failure map and a theoretical approach to forecast the failure mechanisms. Why this idea? We know that the composite joints are characterized by different failure mechanisms because we can observe a net tension fracture when the cracks start and propagate orthogonally to the lower direction, a shear out fracture when we have a fracture of the joint near to the edge of the samples, an hybrid fracture as cleavage that involves net tension and shear out mechanisms, and the usual bearing fracture where we have the collapse of the composite materials just behind the pinned joint. For all of them, the failure mechanism is influenced by the geometry of the samples. And for the joint design, an important parameter is to reach the bearing mode that is the not catastrophic failure mechanism. In the meanwhile, a new direction of the composite materials is to use natural fibers to obtain sustainable composites. From this point of view, the research literature it's really structured with a large amount of papers that use several types of natural fibers. Here is reported as reference a short summary. But the main question is if the natural fibers can be considered suitable or sustainable as a reinforcement. Because from the price point of view and from the weight point of view, we have clearly some advantage to use them because we have an evident reduction in price and weight. But at the same time, we know we have a reduction in performance and also some issues related that the performance of the fibers are also influenced by the site where the plant grow. And the second aspect is the durability, that the natural fibers suffers the critical environmental conditions. And an important point of discussion is to evaluate the stability of these composites during time in this environment. Based on this concept, what is our approach? Our approach is to start to investigate a pinned joint, classical joint. We realized the different composite at varying stacking sequence. In particular, in this experience, flux, glass, and hybrid glass flux composites. We performed the test according to the standard D5961. And for the experimental campaign, we changed the diameter of the hole and also the position of the hole in the sample to change the ratio of E and D to the W is the width of the sample. The same experimental campaign was performed at increasing aging time, 60 until to 60 days in salt fog chamber. Now, concerning the results, the first point that we addressed is to evaluate how the joint geometry influences the failure mechanism. In this slide, we have the stress displacement curve for hybrid, glass, and flux samples for a specific joint geometry that is characterized by a small diameter and small edge distance. In this case, considering that the edge distance is very low, the main failure mechanism is shear out fracture, therefore is a premature fracture. And we see that the stacking segments have a large influence on the mechanical behavior of the joint, because we are a competition between weak natural fibers with a stiff strength glass fibers, the synthetic one, with the hybrid composite that have intermediate behavior with a not catastrophic fracture compared to the two previous one. But when we change the geometry of the joint, the mechanical behavior is totally different. When we consider a same diameter, but we increase the edge distance, in this case, we see that we not have an evident effect of the stacking sequence on the bearing stress. This one is due to the consideration that the failure mechanism changed. In particular, we see that the glass and hybrid glass flux composites evidenced a bearing fracture. Instead, the only natural one with flux fibers, we showed a mixed bearing and net tension fracture. This failure mechanism is also related to the typical nonlinear behavior, because we have the progressive collapse of the composite due to compression stress with the plateau due to bearing stress. Now, considering large edge distance but also large diameter, we have still another mechanical behavior. In this case, the main fracture is, for all of them, the net tension fracture is a premature fracture where the tensile properties of the fibers play a relevant role. In fact, the stacking sequence influence significantly the maximum stress, with obviously the higher behavior for the glass one and intermediate performance with the glass flux. Now, at this point, it was proposed an approach to identify how the joint geometry influences the failure mechanism. Here, I summarized some results where we see that changing the edge distance and the diameters of the hole, we have different failure mechanisms. It's important to see that the net tension fracture, it was observed mainly for hybrid or for natural flex composite laminates. The reason is because for this type of fracture, we have that the stacking sequence have a relevant role in the mechanical performance of the joint. In the meanwhile, also in shear out and cleavage fracture, we have a relationship between stacking sequence of the composites and performance. But after that, we also addressed another aspect of the image, because previously we evidenced how the failure mechanism and the mechanical performance changes at varying joint geometry. In this image, where we related the ratio of working the WD and ED ratios, we indicated the different failure mechanisms that we observed in the map. These one are all samples that were realized in an edged condition. And we see that depending on the joint geometry, the failure mechanisms are clustered in groups. At this point, our idea is to propose a simplified model that discriminates these clusters. Our approach is based on the typical simplified formula for bearing stress, bearing net tension stress and shear out stress. Considering that a mechanism for bearing occurs when the load that we observe in this formula is lower than the other one, we identify that transition between, for example, bearing and net tension, considering that the load in bearing, when is equal to the load in net tension, can be considered as a threshold value that discriminate a bearing to net tension fracture. We obtained these three formulas that we see that this one is a horizontal line in this plot. The bearing to shear out instead is a vertical line, and the transition shear out to net tension is an inclined, a straight line with a slope is reported here, and is in agreement with the experimental evidence that we show. Now, here we summarized the failure maps that we observed experimentally for the different second segments. The flux composite is characterized by the smaller area for bearing. Instead, for glass 1, we have the larger area for bearing, therefore is the most stable configuration. And by using this map, it's possible to identify the bearing fracture for the glass flux laminate can be identified for two specific values of ED and WD ratios. But the important question is if these information are influenced by aging, because we know that the natural fibers have an hydrophilic behavior, therefore favors the degradation of the degradation mechanism of the composite material. Here I summarized the water uptake curves until 60 days for all laminates, with an evident low water uptake for glass, high for the flux 1, we know the typical behavior of the natural fibers, and the flex 1 that have roughly the health value for the two configurations. From the mechanical point of view, we see that effectively we have a progressive reduction of the mechanical performance, the maximum stress decrease due to the edging, but also coupled to the reduction of the mechanical performance, we have a transition, for example, from bearing mechanism to a mixed bearing net tension fracture. And also the displacement increase, indicating that we have a progressive softening behavior that increase the flexibility of the composite or plasticity of the composite. This behavior was observed roughly changing the joint geometry. In this case, I not detail to reduce the presentation. And this one is a new map where we tried to summarize how the edging effect influence the mechanical performance and the failure maps and the failure mechanisms. We compared the maximum load and the displacement at the maximum load in order to have an information of this information and how much switched the curve from the left to the right side of this plot. At the same time, we indicated this one, the unedged sample, and this one are the sample progressively in edged at 30 and 60 days in the salt fog chambers. We see that also the marker increasing dimension, increasing the geometry related to the geometry, the edge, the distance of the geometry. Now we have that for the sample that are characterized mainly to bearing fracture, we see that the unedged one have higher maximum stress, but the other two plots not evidence as a shift to higher displacement. Instead, when we have premature fracture mechanism as neck tension or shear out, we have an evident shift of the curve at higher displacement, indicating that the edging influence the stress-strain behavior of the joint. And instead, for large diameter, the really premature fracture due to neck tension instead switch the behavior of the composite like in the bearing configuration, with mainly a reduction of the load, but with a not significant shift toward lower higher displacement. Then we should talk about the behavior, but is at this point. Also, due to aging, we observe this typical trend. But at this point, we tried to identify the failure mechanism and to relate this failure mechanism to the aging. What is the approach that we used? In particular, we started anyway from our typical formula. These one are the same formula that I showed before, but now they are explicitated to the load. And we see that the maximum load, our hypothesis, is observed when we have the minimum from one of this formula. But at the same time, we also added the cleavage contribute that is shown here, that previously I not indicated. In particular, I considered the cleavage fracture as a mixed contribute to net tension to shear out. Therefore, I determined the average value, and then I considered a coupling index that experimentally was evidenced as 0.83. In the meanwhile, in the formula, we also did some parameters for shear out, net tension, and bearing that were related to the edging contribute, determined experimentally considering the variation of the bearing, net tension, and shear out failure stress at increasing edging time. At this point, we identified the load at the minimum load to observe the failure mechanism, and we were able to determine the line that identify not only the failure mechanism, but also the maximum load. This one compare the experimental data that are the marker reported here with the theoretical one that are the dotted line. Effectively, we see a good relationship between the two models on the load, but mainly also in the failure mechanisms, with an error that is in the range of 5 to 8%. Here I show the failure map in 3D of edged samples after 16 days, with the marker are the experimental one, and this one is the model obtained by using this formula. And therefore, we validated that the system is suitable to discriminate the failure mechanisms and the maximum load of the joint at varying joint geometry. The last step of this activity is an idea that by performing the test at increasing edging time and considering in which way the failure mechanism changes, is possible to try to realize a three-dimensional failure map that can be used to identify where is stable a specific failure mechanism, as for example the progressive one that is bearing. At this point, summarizing, we can switch the conclusion in two sections. A first section related to the unedged configuration, where it's possible to evidence that this approach can be used to evaluate in which way the sample geometry, in particular in this experience, the E sub D, therefore the edge distance to diameter and the width to the whole diameter ratio, influence the failure mechanism, and also to propose a simplified approach to forecast this failure mechanism, and therefore support also the joining designer to identify the threshold value of the joint geometry to obtain the progressive fracture of the joint. In the meanwhile, the edging contribute play a relevant role in the degradation of the joint, and this degradation influence the complex failure mechanism that occur in the pinned samples. And in this case, the theoretical approach that we applied required the addition of an additional parameter related to the degradation index that required to be supported by experimental data. But anyway, adapting this approach to the edging information is possible anyway to have a theoretical model with reliable performance. Thank you for your attention.
Luigi, because you are the chair of the stream, so let me take the lead. If there are no questions, just I have one, Luigi. It's a corrosion conference, so is there any environmental effect in the story that you presented?
Now, of course, the degradation aspect of the composite material is a critical point. This one is a part of our activity that we are working in Messina together with other partners. And our feeling is that specifically for composite materials, the degradation of the constituents, matrix and fibers is the critical point, and in which way this failure mechanism occurs. And this one is one aspect. In the literature, we saw something about to use coupling agent to reduce the diffusion of water at the interface. And this one is our idea. But at the moment, we are thinking that the degradation mechanism should be switched in two groups, reversible one and not reversible one. Therefore, our idea is to give a further improvement on this approach, trying to discriminate how much of this degradation mechanism are critical effectively for our composite material. Because, for example, if we edge one sample only for 1 day, we absorb water easily for a flux laminate, but is reversible because it's only superficial water.
Good. Thank you, Luigi. And now floor is yours. You are the chair of the session anyway. Yeah.
Thank you to everyone. We can switch to the second presentation. Professor Fabrizio Sarasini is associate professor at Sapienza University of Rome. He worked in material science and technology field, and mainly his experience is related to the dynamic behavior of structural composite materials, and with a specific attention to natural fiber composites. His talk have as a title Environmental Effect on Impact Damage Resistance and Tolerance of Composites Laminates. Fabrizio.
Okay, so thank you very much for the introduction, Luigi, and first of all, I would like to thank you because for inviting me and for giving me the opportunity to talk about the environmental effects on the impact damage resistance of composite laminates, and as you mentioned, with a special focus on natural fiber composites. So over the years, the global composite market is increasing a lot, and it is expected to grow at an expanded annual growth rate of about 7.6% from 2020 up to 2027. And basically, we can say that this significant market growth is mainly driven by the need for lightweight materials. Okay, and this occurs especially in some specific industries, such as, for example, the automotive and transportation in general, but also wind energy, defense, and aerospace. The problem is that related to the use of composite materials, there are two main concerns which are perceived as very, very important. And one is the environmental concern. Environmental concern, which is related to the pollution coming from the energy-intensive processes which are used to manufacture fibers, to manufacture polymers and composite materials. And we have also to add the waste disposal problem, which is related to the disposal of these composite materials once they reach their end of life. And the other big issue is a much more scientific, technological one, which is related to the extensive, significant vulnerability of composite materials to impact damage. Impact, if we want to give a formal definition, can be defined as the relatively sudden application of an impulsive force to a limited volume of material. The problem with this definition is, of course, the fact that these two words, relatively and limited, they can be subject to a wide range of interpretations. But in this specific presentation, I will be referring to low velocity impacts as those impacts which occur with a speed lower than 10 meters per second. Okay, so the next step is to understand why a low velocity impact can be a serious threat to composite materials. First of all, because these kind of events can occur in everyday life of a composite material, during manufacturing, during maintenance, during operation. And the biggest difference of composite materials compared to metal structures is that metal structures can usually absorb a large amount of energy by plastic deformation. But when we deal with composite materials, there is no plastic deformation, or at least it is very, very limited compared to the plastic deformation of metals. And in addition to this, composite materials usually show a pretty low transverse and interlaminar shear strength. And another problem is related to their laminar construction. Okay, so if we put together all these issues, we can easily understand why composites are so prone to impact damage. And basically, the brittle nature, the brittle failure mechanism of a composite material, together with its heterogeneous and non-isotropic nature, give rise to 4 major modes of failure under an impact event. They can be matrix mode, they can be a delamination mode, which are produced by interlaminar stresses. It can be a fiber mode or a penetration, when actually we get the final perforation of the specimen. So as you can see here, these different damage modes can be operative at the same time in a composite material. So the resulting damage scenario can be pretty much complex. And here you can see just a schematic view summarizing the typical damage that we can find in a composite material, where we have bending cracks, where we have shear cracks, and these cracks usually trigger the nucleation and development of extensive delaminations. Okay, the problem with these delaminations is that they can severely reduce the strength of a composite material, but at the same time, they can go easily undetected by visual inspection, because in many times, as you can see here, they are located inside the specimen. So on the surface, you cannot see anything, but instead you have a significant damage inside. And so the post-impact residual strength of the composite laminate is usually significantly reduced. And in addition to the impact damage and to the vulnerability of composite materials, we have also to mention that these composite structures, during their service life, they are usually exposed to a wide range of hydrothermal conditions. And these hydrothermal conditions can cause, for example, chemical changes in the matrix material. They can, for example, destroy the fiber matrix interfacial adhesion. And so it is expected that these effects can completely change the mechanical response of composite materials, not only the post-static performance, but also the dynamic response. And if it is true that there are a lot of studies dealing with the effects of a low velocity impact on composite materials, or studies dealing with the environmental aging on composite materials. Instead, I mean, they need to correlate the aging effects with the impact resistance of a composite material has received a limited attention in literature, and despite there are some studies, and here, for example, you can see the typical water absorption curve of a standard conventional composite materials based on carbon fibers embedded in an epoxy matrix. These composites were actually subjected to water absorption in water at 71 Celsius degrees for a pretty long time, over 400 days. So here you can see the typical water absorption curve. And we have to mention at first that composites usually follow thickened behavior under water absorption. And here you can clearly see these results. But one point here we need to mention is that when we have composite materials, conventional, synthetic composite material, you can see that the level of absorbed water is usually pretty low. So it's around 1.2, 1.4. So pretty low. The problem is that despite this very low water absorption, here you can see the impact response curves for dry and wet specimens. And again, despite the pretty low water absorption, you can see that there is, for example, an effect on the impact response curves. In this specific case, the threshold load of the wet specimen was significantly reduced compared to the dry specimen. And a much more important issue here is the extension of the delaminated area. So here you see, for example, a comparison of the delaminated area obtained by ultrasonic C-scans. And you can see that the delaminated area for the wet specimen was smaller than the delaminated area for the dry specimen. And this is basically related to the fact that the composite material became much more compliant. So it was, we can say, toughened, softened by water absorption. And this is related to the fact that the water can, in this specific case, significantly reduce the glass transition temperature of the epoxy matrix. Okay, and this is clearly seen in this picture here. In this picture, we have the compression after impact strength as a function of temperature, because usually when you have an impacted sample, if you want to measure the damage tolerance of this composite material, you can easily perform a compression after impact test. And if we look at this table and this graph in this specific case, we can see that if we perform the compression after impact test at pretty low temperature, we can say up to 100 Celsius degrees, there is no significant difference between the strength retention of the dry and wet specimens. The situation is completely changed at high temperature. So in particular, in this specific case, the authors performed the compression after impact test at 177 Celsius degrees. What we can see here is that at this specific temperature, the wet specimen behaved in a completely different way compared to the dry specimen. And the behavior was significantly reduced. Okay, why this happened? This happened because actually in this specific case, this temperature was higher than the glass transition temperature of the dry epoxy matrix. Okay, so in this case, the damage mode was completely changed by the water absorption, and in particular, it was no longer the impact-induced delamination to control the failure of the composite material, but instead it was the bucket. Okay, and so the damage was completely changed. And this is important to highlight because, as I showed you, in this specific case, for conventional composite material, the level of water absorbed was pretty low. And this is expected to be much more significant when we deal with natural fiber composites. And firstly, because natural fibers show some peculiarities in their microstructure and in their mechanical properties. And here you can see a very nice sketch of the structure of flax fibers. And as you can see here, these natural fibers usually show a hierarchical structure, okay, that spans from the macroscopic up to the nanoscopic scale. So we can consider a natural fiber as a composite itself. So it's pretty complex. It's behavior. And in addition to this hierarchical structure, natural fibers also show properties which are highly dependent on the chemical constituents, and in particular on the relative proportion of the chemical constituents. And basically, natural fibers are composed of hemicellulose, lignin, and cellulose. These are the three main chemical constituents of a natural fiber. And then here in this picture, you can see how these different chemical constituents can affect not only the mechanical properties, in this specific case, the strength, but also the, I would say, the degradation properties of these fibers. So in terms of moisture absorption, UV degradation, thermal degradation, and biological degradation. So this is another issue that we need to consider. And as Luigi mentioned in his presentation, there is also a very strong effect of moisture on natural fibers. And this is something that it is not observed with conventional fibers. So carbon fibers, glass fibers, that do not tend to absorb water. But this is not true for natural fibers. Natural fibers are mostly hydrophilic. And what happens with natural fibers is that they tend to absorb a large amount of water. And when they absorb water, they tend to undergo swelling. And what happens is that this swelling creates matrix microcracks around the swollen fiber, and these microcracks can actually make capillary actions much more easier. And so we have much water which is actually attracted to the fiber itself. And when this fiber actually reaches the fiber matrix interface, what happens is that the fiber is pretty rich with constituents which can be easily solubilized by water. And so we have a significant degradation of the fiber, and at the same time, a significant degradation of the fiber matrix interface, which actually leads to ultimate fiber matrix debonding. So it is expected that the mechanical properties will be significantly affected by the presence of water. And if we combine the effects of environmental aging with low velocity impact, we can expect some, I would say, very bad results for natural fiber composites, simply because natural fiber composites, they do already show lower impact resistance compared to synthetic fiber composites. And here, for example, you can see the results for a composite material based on epoxy reinforced with a plain woven hemp fabric. And as you can see here, when we performed tensile strength tests after an impact, even an impact at low energy, 10 joules, you can see that the decrease in the mechanical properties can be pretty significant. So let's imagine what happens if we combine environmental aging with the low velocity impact on a natural fiber composite. And this is something that we have investigated. In this case, we actually considered jute fiber composites. And of course, in an attempt to reduce, for example, the effects of environmental aging, we try to solve this issue by hybridization. So basically, what we did is to hybridize jute fibers with basalt fibers. Basalt fibers, in this case, are fibers, natural fibers of mineral origin, but they show mechanical properties which are comparable with the properties of glass fibers. And of course, they do not absorb a large amount of water compared to jute fibers. And these composite materials were realized in two different hybrid configurations, a sandwich configuration and an intercalate configuration. The difference is simply how we stacked the different layers together. And this composite material was subjected to a salt spray fog test up to 90 days. And then we analyzed the results on these composite materials from a quasi-static point of view, for example, performing flexural and tensile tests, and also analyzing what happens when we subjected these composite materials to a low velocity impact. So in this case, here you can see the effect of this aging on, for example, on the Young's modulus. We can see a significant decrease for jute-based composite. This decrease was somewhat reduced by the presence of mineral fibers, such as basalt fibers. And of course, the same degradation occurred for the strength, but a point of significant interest is the fact that due to the moisture absorption, which is related, I would say, to the jute fibers, the problem is that the composite material became much more compliant. Okay, and this is also pretty evident here in this picture, where we have the elongation of maximum stress, which actually increased with increasing aging time. How these actually affect the impact response of these composite materials. So here you see a comparison between the force versus displacement curves after an impact event at the same level of energy, 10 joules in this case, for the three different configurations. And in all pictures, the solid curve actually represents the unaged behavior, and the others the aged behavior 30 and after 90 days. So just looking at these curves, I think it's pretty clear that there is an effect on the impact response due to the aging. And this is mainly related to the absorbed water by jute fibers. And this is even more evident when we compare the damage modes that can be easily detected by visual inspection. So here you have again the comparison between the three different configurations. So jute and the two hybrid configurations, all impacted at 10 joules. And in this specific case, these are the results for the unaged specimens. Okay, so even an impact at 10 joules can create significant damage on the front and also on the back surfaces of these composite materials. But what happens when we perform exactly the same impact test on the samples which were aged? Here you have the comparison between jute and the sandwich configuration. So if we compare these pictures with the previous pictures, we can see that in this specific case, the damage on the front and also on the rear surfaces can be hardly detectable. So this actually suggests a change of the damage modes. In the previous case, these damage modes were mainly in the form of delamination and surface cracks. But in this case, we don't see this kind of damage modes, but the damage modes were mainly concentrated inside the specimen in the form of degradation of the fiber matrix interfacial adhesion. Okay, so this is something that is really interesting with these natural fiber composites, and these are instead some pretty new results on this time flux epoxy composites. These composites were tested at different impact energy levels, and this time we try to address the effect of temperature. So during the impact, we changed the temperature, and so these impacts were performed at room temperature at -40 Celsius degrees and at plus 60 Celsius degrees. And again, if we look at the force versus displacement curves, I think it's pretty clear that there is an effect of the temperature. And there is also an effect, for example, on the damage modes. These are the resulting damage modes on the front and back surfaces for the different levels of impact energy at the different temperatures. And for example, if we look at what happens at 4 joules, we can easily see that when we move from -40 up to plus 60 Celsius degrees, for example, the damage on the front face is completely different, and it is hardly detectable here at plus 60 Celsius degrees. So this means that actually at this temperature, the composite became much more compliant. Okay, so on the back surfaces, we didn't detect a significant change in the damage modes because there is always the presence of these cross-shaped micro cracks. And the problem is that are these micro cracks that actually govern the final failure of the composite, because once impacted, we have also performed 4-point bending tests, so after impact, just to assess the damage tolerance of these composite materials. And here you can see the results in terms of the flexural modulus and of the flexural strength as a function of the impact energy. So the fact is that, of course, there is a decrease in these properties with an increase in impact energy, and this is pretty standard. The problem is that we didn't detect any clear trend with the operating temperature. Okay, so this is probably related to the fact, as we have seen, that these composite materials are characterized by a strong localization of the damage. So basically, in these composite materials, the laminations are really limited compared to standard and conventional composite materials. So it is expected, due especially to this strong localization, that in the presence of the cross-shaped macro cracks, that the temperature is not able to change, okay, the failure mode. That's why we didn't detect a significant effect of the temperature on the residual properties. But by the way, the temperature had a significant effect, for example, on the energy absorption ability of these composite materials. And these are all issues that, according to my point of view, need to be further investigated, because I mean, in literature, there are few studies dealing with these issues. So to conclude, I can state that there is an increasing need for combining environmental issues and improved mechanical performances of composite laminates. And this is true in different environments under different loading conditions. And in these loading conditions, impact for sure is one of the most important to address. A viable solution to mitigate, to solve the environmental issues could be the use of natural fiber composites. But as we saw during this presentation, these kind of composites show pretty particular behavior, okay, in terms of their microstructure and also their mechanical properties. And if we focus on the impact response of these natural fiber composites, we can say that in this specific case, usually the lamination is not envisaged as a detrimental, as a significant failure mode, as it happens in synthetic composite materials. And this is mainly due to the fact that these natural fibers show a pretty low transverse strength that tends to localize the damage and triggers the development of significant macro cracks. Okay, so what we have to do in the future is, of course, if we want to widen, if we want to broaden the application of these natural fiber composites, we need for sure to investigate the effect of environmental aging in an attempt to correlate the effect of these environmental hydrothermal conditions on the impact resistance of these composite laminates. And this is just to thank some colleagues and all of you for your attention.
Thank you, Fabrizio, for your interesting presentation, and also you stayed in time. I have one or two questions, because concerning the impact on effectively the damage mechanism are very, very different, competing and so on, and influence the behavior. And this aspect became critical considering the degradation phenomena of the material. But for your opinion about composite structure as a sandwich, where we have a soft core, therefore we have a skin and a soft basement. Your opinion if the degradation mechanism could influence in critical way a brittle skin or a flexible skin as the natural one?
But in this,
your feeling.
Yeah. In this case, when you have a sandwich composite structures, in my opinion, the most important part here is to consider the adhesion of the skins with the core. I mean, we have performed some investigations on natural sandwich structures using, for example, agglomerated cork as a replacement for standard polymeric foams. Okay, and in this specific case, what we detected is, a very critical part is the adhesion between the skins and the core. Because actually, when you have a sandwich structure, especially under an impact event, the damage scenario can be even much more complicated compared to the damage scenario that we have in a standard composite laminate. Because you can have damages not only in the skins, not only in the core, but also at the interface between the core and the skins. And according to my point of view, the most critical part is the interfacial adhesion between the core and the skin, especially if you have a significant mismatch between the stiffness of the core and of the skins. So in this specific case, you can have already residual stresses after the manufacturing process, and these stresses can be even made worse due, for example, degradation phenomena, or for example due to thermal exposure. We can actually increase these residual thermal stresses, and you can easily get the bonding between the core and the skin.
Okay, thank you. And my second question is related about the post-impact properties of the edged samples. Some consideration about that.
Yeah, this is a good question, because there are very, very few works dealing with post-impact damage assessment, especially with natural fiber composites. So basically, the problem with these composites is that if you want to assess the damage tolerance, usually you should perform a compression after impact test. The problem is that, especially when you have, for example, composites that have been subjected to water absorption, what happens is that they become too much compliant. So when you basically try, for example, to perform a compression after impact test, the problem is that you don't get a failure by compression, but you get a failure by buckling. So even if you have guides that actually prevent buckling of the specimen, when you have a specimen which becomes very compliant, it is very, very difficult to induce a failure by compression. So usually, even if you have delamination in your sample, in many cases, it can happen that the final failure is not due to the propagation of that delamination, but is due to buckling in the specimen. So this is something that can be overcome if you change the way you test the post-impact residual property. So in many, many cases, you can perform a bending test, or you can even perform a tensile test. But the compression after impact test, which is a standard for aeronautical applications, usually in these cases, it's not very easy to use, especially with natural fiber composites. Mm-hmm. So it's pretty easy to use with, for example, with carbon-based composite materials, because they are pretty stiff. The problem is that when you use natural fiber composite, especially after aging, you have a composite that can be too much compliant to be tested under compression loading conditions.
Yes, because we have a larger deflection, and it's easier to obtain buckling.
Yeah, and so you get buckling, and in this case, you should consider invalid.
Should be an interesting activity, because effectively, as you said, we don't have a large amount of papers.
No.
We have a lack of knowledge about the durability of the material in this specific area.
And of course, there is also another, research work to be done in order to reduce, for example, as you were mentioning before, to reduce the water absorption in natural fiber composites, especially if we want to use these composites outside. So, in environments that can be harsh, for example, marine environments. So there is a lot of work to do in order to basically to modify the surface of these natural fibers in order to reduce the water absorption, which, according to my point of view, is one of the most critical points as regards the durability of these materials.
Okay, thank you, Fabrizio. Now, in our time schedule, we have the next presentation by Professor Hom Dakal. Hom, are you here?
Sadly, we couldn't contact Professor Homnath Dakal, and he didn't answer any of our reminders, so maybe we should move with the program.
Okay. At this point, we could choose to continue to the program with the idea is to introduce the work of Professor Fábio Fernandes, because we know then we talk about the presentation of Professor Rangappa. Fabio, I saw that you are here.
Yes, good morning. Sorry,
Hi,
I was...
Now, Professor Fabio Fernandes is a researcher at the University of Aveiro. His main research fields are in constitutive modeling and material characterization, and of course, materials for safety application. His talk is an interesting talk on cork composite degradation, in particular exposure to ultraviolet.
And thank you, Professor Luigi Calabrese, for the introduction. Good morning, everyone. I have here the work entitled Cork Composites Degradation and Exposure to Ultraviolet Radiation. This is a joint work with some colleagues from Aveiro, and also a collaboration with a colleague from Aalto University. So first, a brief introduction about cork. So why cork or cork composites? So this is interesting and important material for Portugal, for our country. So cork is the bark of the Quercus suber tree. So this is an evergreen oak. This type of tree grows in several Mediterranean countries, but mainly in the Iberian Peninsula. And Portugal at the moment, if I'm not mistaken, is the largest manufacturer of cork products. So this natural material is harvested in a sustainable way by manually cutting the bark, by extracting the planks from the tree without harming it. This is a process that is usually done in a traditional way by skilled professionals. So why cork is an interesting material? It's lightweight, it's remarkably compressible. As Professor Sarasini said, for instance, it's interesting to use it as a core in some sandwich structures. Especially thinking about green composites, and it's lightweight and compressible thanks to its microstructure and chemical composition. Cork is also wear resistant and is an attractive material for designers, for instance, thanks to its thermal comfort, for its soft touch and appealing aesthetics. Good quality cork is usually used in production of cork stoppers, and this is something that happens, I think, since 2 millennia. So we are using cork stoppers for bottling wine for a long time. Cork with lower quality for stoppers production and recycled cork are usually not wasted, so we can manufacture other composites for flooring, insulation, sealing, sporting goods, even for some parts of shoes, among many others. So currently there are several applications for this material, mainly thanks to its properties, of course, and to the development of new cork composites. As an example, in our group, thanks to the remarkable mechanical behavior and properties of cork composites, we have been exploring the use of cork composites in many applications, also for structures under impact and, for instance, in protective gear. So talking a little bit more about why cork has these mechanical properties or even these thermal properties, where they are good for thermal insulation. It can be explained by its cellular microstructure and chemical composition of the cell walls. So the prismatic closed microstructure of this material was first reported by Robert Hooke in the 17th century. The solid volume fraction corresponds to 15% of its total volume, which explains its low density. Cork cell walls have usually a thickness of 2 micrometers, and they are mainly composed of suberin in association with the lining and the lesser content of polysaccharides such as hemicellulose or cellulose. Suberin is important in the properties of cork because it's a lipophilic biopolymer and is responsible for its elasticity and compressibility. And basically it's kind of viscoelastic behavior and relaxation properties, as well as also the impermeability and also the resilience of this material. And of course, the other constituents are also important. For instance, the lining gives the structural stiffness to the cell walls. So, thanks to its mechanical and thermal properties, and also aesthetics and sustainability, cork composites have been used in outdoor applications, from sculptures to building facades, urban furniture, among many others, and as well as other products that are also exposed to the environment. So there is one question that needs to be answered, since there is this kind of exposition to environment. What happens to this kind of composites and their properties when exposed in the long term to UV radiation? So, and as the aim of this study was to analyze the effects of UV exposure on cork composites, specifically on 3 major points. So the aesthetics, so in terms of visual aspect, the mechanical properties, and the thermal properties. So to do that, the methodology consisted in submitting cork composites to accelerated weathering tests, but in this case, just focusing on UV, followed by mechanical testing, thermal testing, and FTIR and SEM analysis. So in order to assess the resistance to UV, a commercial cork composite was used. This one is manufactured by compression molding, using cork granules around 0.5 and 1 millimeter, and thermosetting polyurethane binder. This results in isotropic specimens with an average density of 200 kilograms per cubic meter. And due to the limited dimensions of the accelerated weathering chamber, we had to stick with 8 millimeter thick sheets for exposition to UV. So we have a limited thickness. So first we submitted the samples to UV exposure in the QV accelerated weathering tester to simulate the damaging effects of sunlight. UVA lamps for a wavelength of 340 nanometers were employed, corresponding to an irradiance of more or less around 0.68 watt per square meter, which is equivalent to noon summer sunlight. And then this makes it possible to obtain quick results without sacrificing the correlation. So the samples were exposed during 4 weeks, so in a total of 672 hours at 40 degrees Celsius. These lamps were selected because they make it possible to realistically reproduce the damaging effects of sunlight that can occur between 300 and 400 nanometers, which typically causes the most weathering damage to materials exposed outdoors. So after exposition to UV, samples were subjected to mechanical testing, thermal analysis, FTIR, and SEM analysis. The same sample size was adopted for all of these kind of testing and analysis. In all the analysis, the non-exposed samples were also tested as a reference for comparison and assessment of the changes caused by exposure to UV. Uniaxial compression tests were carried out at glass static strain rates, a speed of 1 millimeter per minute, in order to analyze the changes in the stress-strain relation. The thermal analyses were also carried out in order to determine the thermal conductivity, thermal diffusivity, and the volumetric specific heat. Each analysis took 80 seconds at a power of 11 milliwatts. FTIR spectra was also required to assess possible changes in the characteristics of the samples using an FTIR spectrometer equipped with an ATR accessory. The morphology of both types of samples was also assessed by SEM equipment. So in terms of results, one thing was immediately clear. So the aesthetics of this composite were clearly affected by the UV radiation. So we can see the discoloration between the exposed region and the non-exposed region. So the degradation of the surface was evident at the macroscopic level thanks to this discoloration. So in terms of color, this was more than evident. So now in terms of mechanical testing regarding the compression tests, here and from this point it is presented average results, but good repeatability was achieved. So in these tests, we can see that the samples exposed to UV exhibited higher stress levels. Although the difference is almost insignificant for small strains, this difference increases with the strain, being maximum at the densification stage. So the exposed UV samples presented always higher stress plateaus as well as sooner densification. So it is possible to observe that samples exposed to UV showed a higher compressive strength, and this reached densification for strains 5% lower than the ones necessary to cause densification in the non-exposed specimens. Regarding the thermal analysis and focusing on the typical application of cork composites as a thermal insulator, as it is possible to confirm by its thermal conductivity, diffusivity, and volumetric specific heat, we can verify that there is some degradation of its thermal constants. So the conductivity, diffusivity of samples exposed to UV increased, while the volumetric specific heat decreased. Although this means that the specimens exposed to UV have a lower capacity as a thermal insulator than the non-exposed ones, the variation is very small and the degraded composite can continue to be used as a thermal insulator. So this was the main conclusion from the thermal analysis. And finally, from the FTIR and the SEM analysis, in order to check for possible changes in the characteristics of the samples and also changes in its morphology. So the SEM micrographs show clear microstructural changes caused by UV radiation. So we can see that there is some irregularity and collapse of cork cell walls. And we can then try to correlate these observations with what we observed in terms of for instance, mechanical behavior, and especially also the observations from the FTIR spectra, which clearly shows some changes, even for samples exposed for 2 weeks. So we took one of the samples earlier just to check what happens with 2 weeks of exposure. But in both cases, there is a decrease in the peaks. And for instance, the one or the ones actually that correspond to suberin, which explains most of the changes and degradation observed in these experiments. For instance, the mechanical behavior in terms of compressive strength and densification. So the main conclusions of this work is that ultraviolet radiation causes changes in the microstructure of cork, which reflects in its macroscopic properties. The changes are clear in terms of discoloration. Regarding mechanical properties, the compressive strength increased, although there is a clear loss in terms of viscoelastic and the compressibility related to the suberin content. And the degradation of its capacity as an insulator was observed, but the magnitude of this effect is almost insignificant, at least for the time of exposure that we employed in our experiments. So I want to acknowledge FCT and the European Union for supporting this research, and also acknowledge ACC for supplying the materials. And that's it. So thank you for your attention.
Okay, thank you, Fabio, for the presentation. I have one question. If you can talk a little bit deeper about the degradation mechanisms of the cork material in ultraviolet condition, and also to summarize some applications, because I know that you work, for example, with mortars or something like that in civil application, because it could be used also in this field. And please add something on these aspects.
Okay, thank you, Professor Calabrese. These are nice questions. And regarding the mechanism of degradation of cork, so what I can say about it is that basically it's all related to the microstructure and chemical composition of cork. So what gives this special, I would say, non-linear elastic behavior, for instance, focusing on the mechanical behavior of cork, is its chemical composition, mainly focusing on the contents like suberin, and mainly suberin, and also lignin. And what we saw from these 4 weeks of exposure, and I must stress this was a preliminary research, is that in fact suberin and lignin are affected. So this was clear in the FTIR analysis. They are affected by UV. And we tested also other composites, cork composites. So this was just one type, where we could see in basically in all these composites that the suberin peaks in the FTIR were influenced by the degradation, so by the UV exposure. And by losing this mainly constituent, so what happens is that the cell walls will lose this kind of viscoelasticity. So we could see that the samples were a little less, they lose some kind of compressibility. So we couldn't compress it as much as we wanted, or for that we needed to employ higher loads. So this was necessary. And regarding the second, oh no, I just thought, sorry, I will go back. Regarding the thermal aspects, I could say that the same justification can be employed. We didn't test one thing, but I think it is something that can be addressed in the future. So is that suberin gives this kind of impermeability to cork. And after exposing to UV, so we saw that we will lose, we'll have some degradation, and suberin will be affected. So cork can be also can have some problems in terms of its impermeability after being exposed to UV. So this might be also another issue if we think about outdoors exposition when UV and water are combined. But this is something to address in the future. Regarding other applications, so right now in terms of outdoor applications, you can see, for instance, in the cork is being used in the building facades. And actually, I'm not the one right now using cork in mortars and geopolymers. This is one of my colleagues that is also collaborated in this work, so Rui Novaes. But in fact, this material is being successfully employed in this kind of geocomposite. So not just with the typical aggregates, but using also with so more sustainable composites like geopolymers.
Okay, thank you.
Luigi, may I? So, Fabio, thank you very much for your presentation. Very, very interesting. And just a very, very quick question. Because you mentioned that basically most of the degradation is related to the suberin under UV exposure. I was wondering whether also the polymeric binder can play a role in this sense.
I think it might have, for sure, it will have a role, but in our case, in this particular composite, we didn't saw it because so just one part of the composite was exposed to UV, and in this particular composite, so the area of exposition is basically the cork part that is exposed to UV. I would say that more than 95% of the area is cork, and since it's just on the surface, and that's why I stress a little bit about the thickness that we employed, because if we are going for higher thicknesses, the impact in the mechanical properties, in the thermal insulation, I would say that will be even lower. So for thin sheets, I would say that we can see this kind of degradation, but for higher volumes, we might not see it. And in this particular composite, I wouldn't say that the degradation of the polymer would be such a problem. But for other ones where higher contents of polymeric matrix is used, I would say that we might have something to study.
Thank you.
Okay, thank you to Fabio. Now we should have the last presentation by Professor Rangappa. He's a senior researcher at the University of Bangkok in Thailand. But unfortunately, I received an email this night that due to the outbreak in India, he lost a parent and have also other troubles with other parents in hospital. Therefore, he had to come back immediately in India, and she is not able to stay here with us. Some of us know him, and some days ago, he also shared with me his presentation to agree about the activity of the topic. I want only to share with all the participants his presentation. Of course, I cannot talk about his presentation, but this one is the presentation that I received by Professor Rangappa. It's only to show the idea, because I started, of course, roughly about the natural fiber composite in the market, in the literature, and then he stressed his discussion on the durability performance of this class of composite materials, mainly focusing on his experience on the characterization of composites, mainly relating from one side the properties of the constituents. On the other side, and another important aspect is the technology that is used to produce the composites. In this case, he used a compression molding approach or autoclave samples. Based on this experience, then he finalized that the natural fibers can be considered as sustainable materials for composite structure, but have some issues related to performance and durability aspects. For this reason, their final consideration related that to have a real industrial application, an important point of discussion is to how to hybridize these materials in synthetic one. That is in agreement with the other talk presented today, because only in this way is possible to optimize the use of this class of materials, taking into account the relevant performance in terms of green and weight and price aspects, but also with the limited durability performance. And that's roughly the point of his presentation. Here are some of the books where he was editor. Okay, at this point, the session 4 is finished. A lot of time before the time schedule. I apologize for that.
Yeah, thank you, Luigi, for taking the time and the effort to present the last speaker PowerPoint. As Luigi said, now we finish the first session of today with a lot of time for the coffee break, as we missed some of the speakers' talks. And that's it. We will make a break now until 11 in the morning here, so around 45 minutes. So please come back for the next session then.